Hi, my name's Adam Brindell. I put together a demo of the Spark cost-based optimizer, which is a new, powerful feature in Spark 2.2. It's maybe not very well known right now, but can potentially give you a big performance boost without requiring a whole lot of work on your part. So I have a little bit of bio information right here. But let's go ahead and dive in and take a look at this cost-based optimizer. So where did this whole cost-based optimizer come from? Well, in the early days of Spark, and in fact in the early days of most big data technology, the concern was, can we actually come up with some reasonable way to compute over these big chunks of data where every minute or hour or week, depending on the size of your project, we're getting a whole new batch of data. And we want to be able to do things elegantly with data that we're maybe only going to see once or twice, and then very quickly, again, seconds or minutes later, we're going to have to throw that out and do some completely different computation on different data. Right? And because the focus was on dealing with data that's often changing and coming in at a high velocity, the early technologies didn't focus so much on being able to do optimized queries the way traditional analytical databases do. Right? A traditional analytical database, we have some valuable data which we're querying repeatedly, and so it's worth investing in optimizations around that specific set of data. So the early days of Spark, not really anything in terms of those optimizations. Then as Spark evolved, we added a number of optimizers. So there's the famous Catalyst optimizer, which restructures queries. And the Catalyst optimizer is great, but it does not take into account the properties of the particular batch of data that you're operating on. Right? So to be clear, unlike, say, Oracle or SQL Server, the Catalyst optimizer in Spark, this is the structural query analyzer, does not take into account the actual data. It just makes the query behavior better based on standard rules for improving queries. For example, moving filters earlier in the query is almost always a good idea, so we can discard data early on. Now, as time moved on and Spark gained in popularity, people wanted to use it for more and more different use cases, including some that were traditionally supported by analytical databases. And so folks started thinking more about, maybe we can actually add in some of these optimizations based on the distribution of data that we're specifically looking at. In 2016 at Spark Summit, a group of engineers who had been at Huawei demonstrated a prototype they put together of creating statistics over a set of data, using it to improve queries, and this was really exciting stuff. So very quickly, a Jira project was created within Spark to add this capability, and within about a year, it was completed and matured, and was released in Spark 2.2 earlier in 2017 as the Spark cost-based optimizer. Right, so this is different from Catalyst, and it's also different from the incrementalizing query optimizer that's used in Spark structured streaming. So Spark has a lot of optimizers, but this cost-based optimizer is the only one which is focused on the statistics and characteristics of a particular batch of data. So let's take a quick look at how this is going to behave. So one really nice thing that we can do with the CBO is improve join performance. If you work on big data projects that involve joins, you know that those are some of the most painful things to work with. It's hard to get your data arranged so that the join succeeds in a reasonable period of time. And even then, that reasonable period of time is almost always much longer than we'd like. So joins are fairly painful, and doing something more elegant and efficient with joins is always a huge boost. So in early versions of Spark, joins were typically ordered based on their appearance in the query without regard for the size of the data. So if I don't write my query correctly, I could end up doing a really bad join. And again, the reason for this is that when we're writing this program, Spark hasn't seen the data yet. And so Spark can't really figure too much out about that data. because it doesn't own the storage like a traditional database would. But like I said, we want to come up with some kind of compromise where we can, if it's worth it, we can look at the data and do some smarter things. So first, let's set up some demo data, and then we'll look at the naive join behavior, the one that we want to improve on. So in this cell right in here, I'm going to create 3 demonstration tables. They're really simple. The first one has 10 million rows, a column called ID with numbers 0 through 10 million minus 1 in the ID column. We'll call that thing big list. I'm going to make another identical 10 million row table, but this one's going to have 2 columns, ID, and then one called square, which has the square of the ID. So these guys both have 10 million rows. We'll call this thing list squares. Then I'm going to create a small table with just 1,000 rows, and we're going to call this thing small. So let's go ahead and run that. And while this thing is creating this data and writing it out, we'll look at our first join query. So in the next cell, we're doing a join where we go out and grab big list, and then we join against the list of squares table on the ID. So this is a shortcut for an inner equijoin here. And then we're going to go and join against the small table on the ID column. Now, as humans, we know that probably a smart thing to do would be to do a inner equijoin against a small table first, so that we can hopefully get rid of most of our rows and keep our data size smaller. But we're going to see that if we go ahead and run this, that Spark, without any additional hints, is not really going to be able to figure that out because it doesn't really know how big these tables are. Never mind that we just created them, we haven't really stored any metadata about that. So let's go and run this join. You may also notice I'm doing a .collect at the end here. So normally that's an anti-pattern. You typically don't want to collect things unless you're really sure that's what you want to do, because you can end up getting a max result size exceeded error or even crashing your driver trying to bring this data back. What I'm trying to do here is force Spark not to add any kind of limit onto this query, which would be implicitly added if I just tried to show the data or pull back a small number of rows. So instead I'm doing a collect, or I could equivalently write the entire thing out to a file. Basically just want to force Spark to do all of the work here. Okay, so we've got some data. We don't really care about the data, but we do care about how this query was executed. Let's flip over to the Spark UI. So here you can see I'm running Spark UI in Databricks. But if you are running open source Spark, you can find this on the driver port 4040. If you're running in a clustered environment, like for example, if you're running in Yarn, you can get to here through the Yarn Resource Manager. But however you're running Spark, you should hopefully have easy access to the Spark Web UI, because without that, it's pretty much impossible to track your behavior and improve and tune your jobs. So let's go here under the SQL tab. Look at the most recent query. That's the one here at the top. I'm going to click on the description link. And what we're looking at here is a visualization of the physical plan as executed. So if we look at these 2 data sets on top, we can see that we're already kind of in trouble. We've got big list and list squares. The names of the relations are up here at the top. It says scan parquet, default.biglist, list squares over here. Those are the 2 10 million row tables. So we're going ahead and joining those. This is not really what we want to have happen. You can see that involves a sort merge join. Sort merge join is the traditional distributed join algorithm. It works, which is kind of a nice thing to be able to say about it, but it's pretty painful. It's expensive and slow, and if we can do something faster or better, we would like to do that. So here we're kind of doing the brute force solution, 10 million rows on both sides. Then we have the small table over here on the right. You can see on top it says default.small. It's got 1,000 rows, and that's being joined using a broadcast exchange and broadcast hash join. So that's a much nicer way to do a join if we can get away with it. In that model, the data set is small enough to be serialized and sent out to all of the executors, where they can do a join by just doing a hash lookup, right? So this is a much nicer and faster way to do it because it doesn't involve sorting or shuffling. And then we have our final output. So what's the takeaway here? The takeaway is that Spark has successfully done a join, but it hasn't done it in a really smart way. It just sort of did what we punched in without giving us a lot of improvements. So let's go ahead and turn on this new Spark 2.2 cost-based cost-based optimization and join reordering, and see if that improves things a little bit. So why do we have to turn this on with these set statements? Well, in Apache Spark, usually when there's major new features that change the way stuff is going to run, they're hidden behind some kind of config flag for a while, so that if you're deploying this Spark 2.2 in production, you don't suddenly see a huge change in behavior with all of your queries. Usually over time, these things will eventually become the default, and then maybe you can opt out of them, and then in some cases, eventually the options go away altogether and you're stuck with the new behavior. But usually that's staged over a series of releases so that you don't have stuff popping up. In this case, Spark 2.2 has CBO implemented, but it's not turned on by default. So we can set these in our Spark conf or other config locations. Here I'm going to dynamically turn them on by running some SQL statements to do CBO enabled equals true, and then turn on the sub feature join reorder enabled equals true. Now, if we were to run our join again, we wouldn't see any change yet, because in order to get the benefits of cost-based optimizer, we need to compute some statistics on the data, right? This was the whole trade-off with cost-based or statistical optimizations, which is that if we're seeing data and using it maybe just once, it may be so expensive to build our analysis of the tables that we don't get much benefit from using that. But if we know that we're going to be querying tables a lot, then it probably makes sense to go ahead and invest a little bit of work to calculate this. And again, this is the behavior that you're used to having by default in analytical databases, where you can get certain queries for free. You can also build indexes if it's worth the time and the space to do that. And the database is going to keep track of statistics in order to improve your query performance. So Spark 2.2 adds these new SQL syntax here: analyze, table, compute statistics. And we'll go ahead and run that on all three of our tables. So these tables are pretty simple, and this will finish fairly quickly. Now let's go and try the exact same query. So again, we're saying big list, join against list squares. Those are the two big tables, and then join against small. And we'll see if Spark does something a little smarter this time. So we'll go ahead and run that. Okay, so again, the results right here are not that interesting, but if we flip over to the Spark Web UI, look at the most recent SQL command again, now things are looking quite a bit better, right? If you look at the relations up here on the top, Spark has chosen to join big list against small, and that looks pretty good, right? Because this is what we wanted to have happen, and that's because Spark now knows how much space each of these tables is taking, and specifically how many rows we've got and how many IDs we're trying to join on. And we can see that the join against the small table is done using a broadcast join, right? So now we've gotten rid of that initial sort merge join, and we're doing a broadcast join against the correct table. So that all looks good so far. And then we come down here. We do have a sort merge join at the end, but one of the sides of this join only has 1,000 rows, so this should also be not too painful. And we can see that adding the CBO and adding the join reorder, we're doing something a little bit smarter now. So let's take a look at another case, and we'll see if we can do something even more interesting here. So let's see what happens if we take the big list and we join against list squares, but this time, before we do that, we're actually going to filter list squares to keep only the rows where the square is less than 10,000. So what does that mean? It means we're only keeping 100 rows, right? So the IDs 0 to 99 will have squares less than 10,000. So we're going to have 100 rows here. And then we have our small table on the right. So what would we like? Let's think about this for a second. Ideally, we would like, again, to take the table with the fewest rows, so this is the result of the filtering, and join that guy first, and then go ahead and join against some bigger table afterwards. So let's see what happens. And we'll flip back to the SQL pane here. And let's see what happened here. So we've got our big list, and we've got our small, which is the 1,000 row table. And now this doesn't look too good here, right? Because what's happening is we're joining the 10 million row table against the 1,000 row table, and then only later are we joining against the list squares table, of which we're keeping just the 100 rows that I've got highlighted right here. So Spark is doing a little bit better than the naive join ordering, but it's not realizing that the filter condition actually should cause a different execution. Why is that? Well, because we haven't built complicated enough statistics for Spark to be able to predict how many rows will pass the filter. Again, we have to invest some time if we want to do that. So let's say we do. We do actually care about that enough that we want to invest the time. So to do that, we're going to run this SQL syntax: analyze table, list squares, compute statistics for columns, and we'll list our ID and square columns here. And we'll run this. Now what's going on here is, instead of just counting rows, Spark is going to calculate histograms of the distributions of data in those columns. Okay, and the purpose of these histograms is so that when Spark sees a filter, for example, a filter on this square column with a square less than 10,000 predicate, Spark can at least take some kind of guess as to how many rows will pass that filter. And so it will get a good guess at how many rows are involved in the join, and can use that information to do some smarter joining. And let's see if it works. So again, the same exact query: big list against list squares with the filter, and then small. And we'll see if Spark is picking this information up. So the most recent query is number 42 here. And it looks like, yes, we've got improvements, right? We've got big list now against list squares with the output of 100 rows here. And that's being done via a broadcast join, so that's great. And then over here on the right, we've got the small table with 1,000 rows, and that is also being joined via broadcast join. So by putting this all together, we've gotten a bunch of nice benefits. One, Spark is intelligently using our filters and our table size information to rearrange the join. The second thing, which kind of becomes a consequence of that first planning step, is that we don't have any sort merge joins. So the final version of this has 2 broadcast joins, and so on a larger data set, our performance should be really nice. Now, a caveat with that, on a large data set, we may or may not be able to actually broadcast the smaller table. So there's a separate set of rules about when we can broadcast stuff, and some steps you can take to tune that, which we're not going to talk about today. But with the right adjustments and the right planning, if we can get some broadcast joins in there instead of sort merge joins, we'll have a huge performance improvement, in some case multiple orders of magnitude. Okay, so what are the takeaways from all this? So we've got better join ordering. We're able to take into account the distribution of data within the actual tables or data frames or queries, instead of just naive join ordering based on the query structure. And we've been able to avoid some sort merge joins. If you want to learn more about this, there are 2 presentations from Spark Summit 2017 that you might be interested in. We've got these YouTube links right here you can check out. along with the slides that went with those presentations. If you're trying to explain this to your coworkers and you don't want to go through the whole tutorial, but want to just get people's attention, what is the takeaway? Benchmarking performance on the TPC-DS benchmarks. 16 queries show a speed up of over 30% using cost-based optimization. The maximum speed up of any of those queries is 8x, and the geometric mean across all of the speed ups is 2.2x. So quite a lot of practical performance improvements. You can see that the whole point here is we did not need to change our application code. What we did is we invested a little bit of time building stats and made Spark smarter about how to run our existing code. So that concludes our demo for cost-based optimization. Check it out. Do some benchmarks on your own data, and hopefully you can get some performance improvements out of that also. Thanks a lot.